Right, so this is our presentation on membrane technology, specifically membrane separation technology. So let's go into it. So this is how we are going to go about the studies. Like we are going to have introduction, mass transfer, membrane overview, mass transfer, membrane operations, membrane separation processes, membrane classification, synthesis of biomass membrane, membrane characterization, biomass membrane application, and then you look at the references. All right, so to the introduction, membrane technology covers all engineering approaches for the transport of substances between two fractions with the help of semi-permeable membranes. So in general, mechanical separation processes for separating gaseous or liquid streams use membrane technology, right? So in recent years, different methods have been used to remove environmental pollutions like adsorption, oxidation, and membrane separation. So yeah, so membrane technology uses semi-permeable membranes to separate substances in gases or liquids. So playing a key role in removing pollutants from the environment alongside methods like adsorption, I mentioned earlier, and oxidation. Industries must comply with regulations such as the Air Pollution Control and Prevention Act 1981 to minimize chemical emissions. Biomass-based membranes offer a cost-effective, efficient, and eco-friendly solution compared to traditional materials like polysulfone, polyvinyl yeah, if I'm right, fluoride, and polypropylene, yes, which contribute to environmental pollution. Researchers are exploring biodegradable alternatives sourced from biomass and to further enhance sustainability. Yes. Now let's come to the membrane overview. So membrane separation processes use less energy compared to heating based methods like distillation or crystallization. They physically separate substances, yielding both permeates and rentates as usable products, widely employed in food, biotech, and pharmaceutical industries for separations impossible with thermal methods. And they are also essential for protecting sensitive water bodies and recreational areas in medical applications, and also growing importance in environmental protection and modern energy technologies like fuel cells and osmotic power plants. Mass transfer, yes. Two basic models can be distinguished for mass transfer through the membrane. So the first one is solution diffusion model and hydrodynamic model. So in real membranes, these two transport mechanisms certainly occur side by side, especially during ultrafiltration. Now, solution diffusion model. So in the solution diffusion model, transport occurs only by diffusion, yes. The component that needs to be transported must first be dissolved in a membrane. The general approach of the solution diffusion model is to assume that the chemical potential of the feed and permeate fluids are in equilibrium with the adjacent membrane surface, such that appropriate expressions for the chemical potential in the fluid and membrane phases can be equated at the solution membrane interface. The principle is more important for dense membranes without natural pores, such as those used for reverse osmosis and in fossils. During the filtration process, a boundary layer forms on the membrane. This concentration gradient is created by molecules which cannot pass through the membrane. The effect is referred to as concentration polarization, and occurring during the filtration leads to a reduced transmembrane flow that is called a flux. Concentration polarization is in principle reversible by cleaning the membrane, which results in the initial flux being almost totally restored using a tangential flow to the membrane, that is a cross-flow filtration, can also minimize concentration polarization. So this video here is showing the concentration gradient, and then this is filtration, just for us to understand and absorb and assimilate what I'm talking about. Now, the hydrodynamic model. So transport through pores in the simplest case is done convectively. This requires the size of the pores to be smaller than the diameter of the two separate components. Membranes that function according to this principle are used, mainly in micro and ultrafiltration. They are used to separate macromolecules from solutions, colloids from a dispersion, or remove bacteria. During this process, the retained particles or molecules form a pulpy mass that is called a filter cake on the membrane, and this blockage of the membrane hampers the filtration. This blockage can be reduced by the use of the cross-flow method, that is the cross-flow filtration. Here, the liquid to be filtered flows along the front of the membrane and is separated by the pressure difference between the front and back of the membrane into rentate. That is the flowing concentrate on the front and permeates, that is the filtrate on the back. The tangential flow, on the front creates a shear stress that cracks the filter cake and reduces the fouling.
So I'm going to continue from where my colleague stopped. So now we are going to move on to membrane operations. So according to the driving force of the operation, it is possible to distinguish, that is, pressure driven operations. That's one. Microfiltration. So like these are like all types of the separation methods. So we have the microfiltration, we have ultrafiltration, we have nanofiltration. So like one may ask, why is it micro, ultra, nano? So they are all the same type of filtration, but into specification. So we have reverse osmosis, gas separation. So now concentration driven operation dialysis. So we have forward osmosis, artificial lung. So now operation in an electric potential gradient. We have one electrodialysis, membrane electrolysis. That's example, the cycloalkaline process. We have electrode ionization. Sorry, we have electrode filtration, fuel cell, operations in a temperature gradient, membrane distillation. So now let's move on to membrane shapes and flow geometries. So we have different types of membranes and we have different types of shapes and geometries and how the flow and everything occurs in the separation process. So now there are two main types of membrane filtration configurations. You have the cross flow and the dead end. Dead end filtration involves fluid flowing directly through the membrane, making it simple and cost effective for small scale studies. However, it is too prone to fouling and concentration issues due to stagnant flow. In contrast, cross-flow filtration directs feed tangentially across the membrane, minimizing fouling with continuous sweeping of particles. This method is more complex and costly, but suitable for large-scale operations. Common membrane model types include the flat plate for dead end setups, spiral wounds for cross flow with reduced fouling, and hollow fibers offering high surface area in a compact design. Overall, choosing between dead end and cross flow depends on scale, cost, and fouling considerations in membrane filtration. But then I will go for the, I think, the cross flow. because taking into consideration the cost, I'll go in for the cross flow. So let's move on. So the next one is membrane separation processes. Membrane separation processes gain importance around mid 1970s and are crucial in various industries. These processes differ based on how they separate particles and their size. Common membrane processes include microfiltration, ultrafiltration, as I mentioned in the earlier slide, nanofiltration, reverse osmosis, electrolysis, dialysis, electrodialysis, gas separation, vapor permeation, membrane distillation, and membrane contactors. Most processes, except P evaporation, do not involve phase changes. Except for electrodialysis, all processes are driven by pressure. Microfiltration and ultrafiltration are widely used in food and beverage processing, biotechnology, pharmaceuticals, water purification, and microelectronics. As a chemical engineer will say, can work in almost all these industries. That's biotechnology, pharmaceuticals, and water purification. And you can apply all this knowledge learned from separation processes. So now let's move on. So nanofiltration and reverse osmosis are mainly used for purifying water. Dense membranes are used for gas separations like CO2 removal from natural gas and separating N2 from the air. Membrane distillation aids in separating azeotropic composition. So one may ask, what is an azeotropic mixture? So you have something called azeotropic. So azeotropic compositions, a mixture containing different types of elements which can be separated by membrane distillation. And we have what? Reducing distillation costs. Yeah. So now let's see the membrane classification. Biomembrane is classified into two main categories. So the first category is the synthetic membrane. So, so the word synthetic, sorry, which means artificial. And we have the second category, which is the natural membrane. So one, the synthetic membrane further classified in organic and inorganic membrane. Organic membranes subclassified polymeric membranes and inorganic membranes subclassified ceramic polymers. Let's continue. Synthesis of biomass membrane. The composite biomass membrane. Biomembrane synthesis using composite biomass improves membrane performance by enhancing surface hydrophilicity, increasing pore size, reducing surface roughness, and thereby enhancing separation efficiency and antifouling properties. Materials like activated carbon nanoparticles from biomass such as coconut shell, hazelnut shell, walnut shell, and agricultural waste like corn stalks are utilized for this purpose. So if you have some corn stalks in your house, if you're done cooking, don't throw it away. It's very important in the synthesis of biomass membrane. Thank you. So the next one, you have fabrication of pure biomass based membrane. A biomass based membrane is made from organic materials like plant fibers, typically used in water filtration and wastewater treatment. Fabrication involves one, creating a slurry of organic materials. Two, casting the slurry into a substrate, example glass or metal plate. Three, drying the cast membrane. Four, subjecting the membrane to treatment into bracket chemical or heat for property enhancement. And the last one, challenges include achieving desired membrane properties during fabrication. So membrane characterization. So membranes can be characterized into several forms. That is, after casting and synthesis of membrane, there is no need to characterize the prepared membrane to know more details about the membrane parameters like pore size, functional groups, vertability, surface charge, sorry. It is important to know membrane properties so we are able to remove and treat a particulate pollutant, which causes pollution in the environment. For characterization, following the different instruments are used. So we have different instruments which are used to classify different types of membranes. You can research more about them, but I have some here, which is one scanning electron microscope. That's the same. Transmission electron microscope. That's the term. Fourier trans Fourier transform infrared spectroscopy, atomic force microscope, contact angle meter, zeta potential into bracket streaming potential, X-ray diffraction, which is normally used in hospitals, liquid displacement porosimetry, that's the LLDP. Thank you.
Okay, so I'm taking on from here to discuss the applications of biomass membrane. So we all know that biomass membranes have many importances and they have many importances and they are applicable in every stage in our lives, in our daily lives. So one, we are beginning with water treatment. So water treatment is any process that improves the quality of water. So in normal and actual sense, it means that biomass membranes help us to improve the quality of water, to make, for example, waters that are not potable, potable, waters that are not usable, usable. You understand? As we all know, membranes allow particles to pass through them. So it is written here, membranes can be used to remove particulates from water by either size exclusion or charge separation. The next one is gas separation. Membranes are being used in gas separations like carbon dioxide, nitrogen oxides, sulfur oxides. We all know that the atmosphere comprises of many gases. So with the help of biomass membrane applications, we are able to separate the harmful ones from the ones that are not harmful to protect the environment. And the next one is hemodialysis. Membrane application in hemodialysis is a process of using a semi-permeable membrane to remove waste products and excess fluids from blood. So thank you. We are now at our references. So here are some of the books and some of the places where we're able to take our informations from. So in case you want to make any referrals or you want more ideas and more knowledge about what we've discussed. So first we have Osada Y. Nakagawa, Membrane Science and Technology, New York, Marcel Decker Incorporation, 1992. We have Zeman, Microfiltration and Ultrafiltration, Principles and Applications. And also we have Basic Principles of Membrane Technology by Mulder M. And also we have Stereo Filtration by Jonit Malik W. Also we have Process Membrane Technology by Van Rees. Again, we have membrane separation of solids from corn processing streams by this group of people, Templin, Johnson, and Singh. And the last we have here is the microporous membranes in biotechnical applications and also membrane. Thank you very much. Thank you. This is a presentation by Group 1.